Hi viewers, welcome to LMS Solution. Today we are going to see about MATLAB implementation of 30 megawatt grid connected PV system. So this is a simulation model created for a 30 megawatt grid connected PV system in MATLAB. So this model consists of 30 megawatt PV array, and then the 30 megawatt PV array going to be connected to the 3-phase inverter via this boost converter, and then this 3-phase inverter is going to be connected to the 11 kilovolt grid. Okay, 11 kilovolt grid via this filter inductor, and this boost converter going to be designed based upon the rating of PV panel or PV array. That means rating of that power rating of PV array, and then on the terminal voltage of the PV array, and then the voltage requirement in the DC link, that means input of this inverter. So based upon this parameter PV power and the terminal voltage of PV and then DC link voltage requirement, so we need to design the value of inductor, capacitor. So in order to design, during design of that boost converter, we need to take care of switching frequency, and then ripple inductor current, and then ripple capacitor voltage. That means you have to specify the percentage of ripple inductor current and then percentage of the ripple capacitor voltage. So based upon these things, so you have to design that inductor and capacitor. And then so here we are connecting that PV for generating the power from sunlight, right? And then whatever power we are generating, right, from the PV, so that going to be given to the grid, right? That means that going to be injected into grid. That means it going to be injected in the form of real power. Okay, so already all of you know about something about PV array. That means the PV array having non-linear characteristics, so we need to extract the maximum power from the PV. That means, so here I will explain via that PV IV characteristics, right? So this is a PV IV characteristics of that consider PV array. So here you can see that the PV curve going to be changed with a different wave irradiation, right? So when you have to operate the PV panel with a different voltage level, so you can see that if we are going to operate the PV panel at 1000 watts, so this is a PV power we are getting. For example, the current irradiation equal to 1000 watts per meter square, and then PV operated at 1000 volt, then we are getting around only 6 megawatt only, but the actual peak power is present here, right? So we need to operate that maximum power point of the PV array. So that means we need to make the PV voltage towards to that point voltage. That means here we need to operate the PV array to 5000 volt, right? So for that we need to use some MPPT algorithm, maximum power point tracking algorithm or peak power tracking algorithm. Okay, so there are several algorithms available in the research, right, and literature. So here we are going to use the conventional or classical method like Perturb and Observe method, P&O MPPT algorithm. So by using that P&O MPPT algorithm, here we are extracting the maximum power from the PV array along with this boost converter. Okay, so for that we need to measure the PV array voltage and current. Okay, so here we are providing the PV array voltage and current, and then it going to be processed via MPPT algorithm, and then it going to provide the duty cycle. Okay, so that MPPT algorithm will be operated like that, right? That means, so here you consider, right, for example I'm going to take 2 point, right? So this is point 1 and this is point 2. So this is going to be considered as V1 and this is V2. Okay, so this is a previous instant, this is the current instant, and here we have the power point, right? That means power level, that means P1 and P2. Okay, so just you have to take the difference of the 2 points P2 minus P1 and V2 minus V1. Okay, that means so this is nothing but del P and del V. Okay, so here you can see that the del V symbol, that means sign of the del V is positive and the sign of del V is positive. If both will be positive, so what will we do? So we need to move the point from this point to this point, right? So we need to increment the voltage of the PV array. Okay, so you consider the same 2 point, right? Now so this point known as V1 and this point known as V2 and this point known as P1 and this point known as P2. Okay, so you take the difference del P and del V. So now the difference, right, that means sign of del P and del V, right, is negative. Okay, so both will be negative means, so what will we do, right? So we need to again you need to increment the voltage from this point to this point, right? We need to increment the voltage. So in both condition we need to increase the voltage, right? So in boost converter we need to decrease the duty cycle. When decrease the duty cycle, we can increase the voltage level. Okay, so these are two set of conditions. So another set of condition, you have to take this direction, right? So you have to take this direction, that means right side, right? So here you consider V1 and so this is V2, so this is P1 and this is P2. So the next you have to find out difference and the sign, right? So here you can see that the del V is positive and del P is negative. When del V, that means when del V is negative and del V is positive, so here we need to move the point from this point to this point. That means we need to decrease the voltage, right? Same case, now you consider this point will be P2, this point will be P1 and this will be V1 and this will be V2, and then you have to find out the difference. Now we can see the difference, that del P is positive and del V is negative. So again we need to move the point from this point to this point. So again we have to decrement the voltage. So here we are decrement the voltage. So here we are using boost converter, so that's why we need to use the that means you have to increment the duty cycle. So based upon this 4 set of condition, the P&O MPPT algorithm is working. So here we have that condition. So here you have to mention 4 condition: initial duty cycle, maximum duty cycle, minimum duty cycle, and then small change in duty cycle. And then here you have to fix the previous voltage, power and that means previous duty cycle. So initially you have to assign V volt, P volt equal to 0 and D reference volt equal to D initial, and here you have to measure P equal to V into I, and here you have to measure the del V equal to V minus V volt and del P equal to V minus P volt. So these are nothing but the finding the difference between current to previous, and that means del V is nothing but change in voltage between current to previous, and del P nothing but the difference between current power to previous power, right? So next you have to check the condition when del P is greater than 0, that means del P is positive and del V is positive, right? So here we need to decrement the duty cycle. So here we need to, that means the system will be operating in the left side, right here. So in this side, that means left hand side it will be operating. Okay, so here we need to increment the voltage, so that's why we have to decrement the duty cycle. So when del V is less than 0, that means it will be operated in the right side. Okay, so we need to increment the duty cycle, that's why we need to decrement the voltage of the PV. Okay, so next you have to check the condition del P is less than 0. Okay, that means is negative, and del V is greater than 0, then here we need to, that means it will be operated in the right side. Okay, so then we have to increment the duty cycle. So that's why we can increase that means decrement the voltage. Okay, so when del V is not greater than 0, so that will be in the left side of the operating region, so we need to decrement the duty cycle. Okay, so here we apply that that 4 set of condition for applying that P&O MPPT. Okay, after calculating the new duty cycle, so that going to be compared with the maximum and the minimum duty cycle. So that the calculated duty cycle is in between that two limits, right? So no need to do anything. If suppose the new duty cycle is more than D max or less than D minimum, then we have to make that the current duty cycle which is equal to previous duty cycle, right? So here we are overrating the current duty cycle power and voltage with the previous duty cycle voltage and power. So this will be keep on executing to extract the maximum power from the PV panel. Okay, so finally here we are getting the duty cycle. That duty cycle going to be processed by PWM generator, right? So just so the for example, this is a duty cycle that going to be compared with the sawtooth waveform or triangular waveform. So that will be generate the pulse. Okay, that will generate the PWM impulse. So that pulse going to be control this IGBT of this boost converter to extract the maximum power from the PV array. Okay, so next to process we have to convert that DC power into AC power, right? So for that here we are using the DC to AC inverter. So the DC to AC inverter will be controlled by means of voltage and current control method. So voltage control method used to for maintaining that the DC bus voltage constant. Okay, and current control used to for converting that DC power into AC power. That means converting the real power. Okay, so it transforming real power from the PV panel to the grid. Okay, so for that we go for current control method. So for that here we have voltage control concept, right? So here we need to measure the DC link voltage. The DC link voltage is compared with the reference voltage. So here we are measuring, that means maintaining the reference voltage which is equal to 20 kilovolt, right? So because it will be connected to the 11 kilovolt grid. Okay, so here you can see that we are connecting the PV system with the 11 kilovolt grid. So 11 kilovolt to 50 hertz grid. So that's why. So here we are taking that DC link voltage is around 20 kilovolt, right? So after comparing that reference voltage with the actual voltage, DC link voltage, so that going to be converted into per unit, and then it going to be processed via PID controller. So that PID controller will be provide the reference current, right, in the form of ID. So this is ID reference. Okay, and then here we are only transferring the real power. So that's why. So the IQ reference will be making. That means here we make to the 0, right? Because we are not sending any reactive power, we are sending only a real power. Okay, and then we are measuring the grid current here, and grid current going to be converted into per unit form, and then here we are converting that ABC into DQ0 form. Okay, so here we are applying path transformation, right? So by using synchronous reference frame theory, so we are converting ABC into DQ0. And then here we are going to control only two parameters, only D quantity and Q quantity. So we are taking only D quantity and Q quantity, and then it's going to be compared with the D reference and Q reference. Okay, so it's going to be compared with the D reference and Q reference, and then again it's going to be processed via PID controller. So this PID controller will be generate the control signal for this PWM generator in the form of D and Q. Okay, so we cannot use the D and Q directly to drive that mean process by PWM generator. So we need to convert the DQ not form into ABC form. So here we are applying inverse power transformation. Okay, so after applying inverse power transformation, so it will be converted into ABC form. So here we will get a 3-phase AC control voltage. Okay, that 3-phase AC control voltage is going to be processed via PWM generator, and then it will be generate the 6 pulse for this inverter. So this inverter will be controlled by means of this voltage and current controller, and the whatever power generated in the PV array, so that will be given to the grid. Okay, so here we have the different kind of measurements. So here we are measuring the irradiation, PV voltage, PV current, PV power, and here we are measuring the DC link voltage, and here we are measuring the control signal from that current controller, and here we are measuring the grid voltage, grid current, inverter voltage and inverter current, and here we are measuring the grid power, inverter power. Okay, so now I am going to control that PV array. That means I am going to change the irradiation. Okay, here I am going to change the irradiation for every 0.5 seconds. Okay, so initially it going to be maintained at 1000 watts per meter square from 0 to 0.5 seconds. After 0.5 second, the irradiation change from 1000 to 100. So it will be maintained 1000 from 0 to 0.5 seconds. After that it comes to 100 watts per meter square, and then maintained for 0.5 seconds. Again it goes to 1000 watts per meter square. So it will be repeated for 0.5 seconds, right? So for that response for changing irradiation, so we are going to see the result of the PV voltage, current and PV power, and then you have to see the result of grid voltage, current and inverter voltage and current, and the grid power and inverter power, and also you have to see the DC line voltage and the control voltage from the system. Okay, now I am going to simulate the model. Now I am going to simulate this model, so you will see the results. So now we can see the irradiation is around 1000 watts per meter square. So the PV voltage is maintained at 5000 volt, right? PV current is around 6000 amps, and then here you can see that we are getting around 30 megawatt power from the PV. So here you can see this is a grid voltage and grid current, and then inverter voltage, inverter current. So you can see that grid current and the inverter current having sinusoidal waveform. Okay, and also here you can see that the irradiation will be now decreasing from 1000 watts per meter square to 100. So because of that you can see that, so there is slight deviation, slight reduction in the PV voltage, and also you can see that as per the irradiation the PV current is decreasing and PV power also decreasing now, and also you can see that there is reduction in the PV current and inverter current, and also here you can see that, so this is a grid power. So initially it maintained at 3 megawatt. So because of reduction in the irradiation, so grid power and the inverter power also decreasing. So this is a variation of DC link voltage. DC link voltage is maintained around 20 kilovolt, right? And this is a control signal. For low irradiation also the grid current and inverter current having sinusoidal nature. There is no distortion in the grid current and inverter current. So after 0.5 seconds, so at 1.5 seconds again the irradiation will be increases from 100 to 1000 watts per meter square. So because of that you can see that, so there is sudden increasing the PV voltage, and also the PV current is increasing now, and here you can see this PV power also increasing, and then here you can see that that inverter voltage is having 3 level output, right? Here also you can see that the inverter power is increasing, grid power is increasing, and current also increasing, right? And also the DC voltage is maintained around 20 kilovolt. So it depends upon that irradiation condition. Okay, so now you can see that now is reached to 1000 watts per meter square. So PV power maintained at 3 megawatt, PV voltage maintained at 5000 volt, and PV current maintained at 6000 amps. So here grid power and PV inverter power will be 30 megawatt, and DC link voltage maintained at 20 kilovolt. Okay, So we are extracting the maximum power from the PV by using MPPT algorithm, and whatever power we are generating, we are generating that power going to be given to the grid. So next I'm going to analyze the system. That means I'm going to check the THD of the grid current and inverter current. So when you are going to connect that PV, right, to the grid system, so the current quality should be maintained. That means the THD of the grid current and inverter current should be less than 5%, right? So next I'm going to check that detail. So for that I'm going here and click tools and click FFT analysis. So here we are measuring the input to that grid current, and then here I'm going to make here you have to place 50 Hz 2500, and then here I'm going to check, that mean at 0.5 second I'm going to check the THD. So THD around only 0.81%, okay, and I'm going to check the THD at 1.2 second. So here also you can see that THD is maintained at 0.86%, okay. Now I'm going to check the THD at 1.8. So this is around 0.47%, right? And also I'm going to check the THD for a inverter current. So here also 0.47%, and I'm going to check the THD at 1.2, and here also you can see that the THD around 0.86%, and I'm going to check the THD at 0.5 seconds, the THD around 0.81%, right? So whatever power generated is going to be given to the grid, as well as the THD of the system, right, maintained is around 0.81%, okay. So the current quality also is maintained less than 5% as per IEEE standard, okay. So this is a working of 30 megawatt grid connected PV system in MATLAB. Thank you for watching our videos. Kindly subscribe our channel and also click the bell icon for notification about upcoming videos. Thank you so much. Bye bye.